Good afternoon and most welcome to 1285 of the H series. And in the previous lecture 1284 we just terminated the longest readout ever in the series. A whopping, let's see how many pages there were. A whopping 348 pages. That is in itself rather amazing. And a tough read on top of that. Many reviewers complain or just comment it's unfathomable. But I think what we had before with constructive mathematics, Wittgenstein, Heidegger, the different cognitive scientists starting with James Gibson, Tony Shimero, Lisa Friedman Barrett, David Bradel and his cerebellum, Barbara Tversky, Lakoff and Johnson, Brouwer, as we studied a long time ago, 2 years ago, the founder of the that brought a lot of understanding to mathematics as well as revealing the Platonic trait in mathematics. Then Newcomb Greenleaf. I would say Kahneman has been very helpful here too. The 1% rule, James Weather, if I recall correctly, very important. And this is following the heritage of Paul Feyerabend without doubt. Both Roberto Unger and Smolin are definitely most worthy inheritors of the legacy of Paul Feyerabend. Such a decent fellow. If you heard anything about this, and speak about decency, in Roberto Unger's homepage you can find his book, but it seemed that he had problem with the copyright of his own book. There is no small and nice PDF file there. No, he copied it by himself. I find here in the readout hairs and fingerprints and other things. In his want to bring these ideas to the public. Odd synchronicity here. Speaking of his copying capability, it seems that he missed a page here of the Smolin thing. This is Smolin starting up, so I don't think anything of value be lost. I will fill you in later on. I do have the book at home. But he's going through sort of the crisis in science in a Feyerabendian way. The crisis, ironically, a measure of success of models written down in the 1970s to explain all the experimental data gained since. In elementary particle physics, that model is called the standard model, and it has been confirmed by all experiments. Make sure it's including the recent observations at the Large Hadron Collider. In cosmology, there is also a standard model, and its predictions have likewise been confirmed by the most recent data. The crisis is due to our inability to go deeper than these models to a further unification of physics, or to explain the features of the models themselves. They reveal a universe that on rational or aesthetic grounds appears preposterous, and each has a long list of parameters which must be tuned very finely to agree with the experiment. Many ideas have been proposed to explain why these parameters have the values they have. None has definitely succeeded. The standard model of particle physics develops a few simple ideas: unification via increased symmetry, and the spontaneous breaking of that symmetry, the gauge principle. These ideas have failed to take us further. The few additions to our knowledge of nature gained since the 1970s fulfilled no theoretical need and confirmed no deeper idea. Neutrinos have mass. There is dark matter and dark energy. These are good to know, but they just deepen the mystery. In cosmology, all observations support a very simple picture of a universe expanding from a hot Big Bang, governed by Einstein's general theory of relativity. but it is an extraordinarily special universe, formed with extremely special initial conditions that tempt us to say we live in an improbable universe. Tempt us until good sense holds us back from asserting that our deepest understanding of the unique, single universe is that it ought never to have happened at all. One way the universe appears to be improbable is that it is highly asymmetric in time, so that a strong directionality to time is apparent in a large spectrum of phenomena over a wide range of scales. This appears inexplicable given the fact that all the known laws of physics are reversible in time. This is an aspect of the present crisis that has been with us since Boltzmann's invention of statistical thermodynamics in the late 19th century. So one way to measure the depth of the current crisis is by the fact that the basic features of our universe, such as its dominance by irreversible processes, appears to be inexplicably based on current knowledge. In this book, Roberto Mangabeira, Unger and I propose a radical solution to this crisis of fundamental physics and cosmology. The road back to reality, we suggest, begins by making two affirmations about nature: the uniqueness of the universe and the reality of time. These together have an immediate consequence, which is the central hypothesis of our program, that the laws of nature evolve, and they do so through mechanisms that can be discovered and proved experimentally, because they concern the past. There are several arguments that lead to this program. In this part 2 of the book, I develop 3 of them. The first goes directly from the data itself, because this preposterous universe with its seemingly inexplicable fine-tunings of parameters, both elementary and cosmological, does make sense if it is seen as the result not of a priori principles, but of a historical and evolutionary process which acted over time and continues to act. The second way into this program comes from an analysis of the basic principle that governs the nature of the fundamental forces, the gauge principle. Both the local gauge invariances that form the weak, strong, and electromagnetic interactions, and the diffeomorphism invariance of general relativity reflect a single idea. Physicists call this idea local gauge invariance, which philosophers of physics understand to be the application of the philosophy of relationalism, the view of nature introduced by Leibniz and developed by Mach, Einstein, Weil, and others, according to which properties of elementary particles rest fundamentally on their participation in a dynamical network of relationships that form the universe. The current crisis in theoretical physics and cosmology can also be understood as a crisis of relationalism, which has two causes. The first is that the program of relationalism, while essential and successful in that it led to general relativity and Yang-Mills theory, faces its own limits. Not every property can be a relation. There must be intrinsic properties which the relations relate. Relationalism is also in crisis because its expression within the usual framework of timeless, immutable laws embodies a tension, if not a contradiction, because the essence of relationalism lies in the relations being dynamical. If the laws are timeless, they cannot themselves be aspects of the developing networks of relations. Yet a basic tenet of relationalism is the idea that everything that acts must also be acted upon. And this should apply to everything that serves as a cause of change or motion, including the laws themselves. The path to resolve the crisis of relationalism is then to make the laws themselves subject to change and dynamics. That is to embrace the reality of time in the strong sense that everything changes. Sooner or later, everything is in the throes of dynamics and history, even the laws of nature. Behind the crisis of relationalism is a larger crisis, a crisis in the naturalist philosophy which underlies the progress of science and technology. They had the idea that all that exists is natural. Physical stuff is more plausible now than ever, due partly to progress of physics and digital technologies, but even more to the triumph of reductionist strategies in biology and medicine. Yet it is in crisis because of an embrace of the old metaphor that the world is a machine. In its modern incarnation, the mechanical philosophy becomes the computational philosophy, that everything, including us, are or are isomorphic to digital computers carrying out fixed algorithms. This leads to the failed, but to its proponents, and this is important, inevitable program of strong artificial intelligence, and also to the identity theorists in philosophy of mind, who proclaim that conscious experience, agency, will, and intentions are all illusions. This third crisis of naturalism is explored elsewhere, and I will put in parentheses here, it's an inevitable program. Remember that. And this shows that all criticism of the likes of Daniel Dennett is wrong. because it is an inevitable program of what is already established before the criticizes and Dennett himself started to do philosophy. But it is becoming increasingly apparent that we are not gadgets, and neither is the universe. We would like to have a naturalism that does not reduce human experience and aspirations to illusion. At the very least, we need a naturalism that does not straitjacket our understanding of complex systems such as the human brain, to fail metaphors coming from an early 20th century formulation of what it is to make a computation. Why can't the brain be a physical system that does not happen to be a programmable digital computer? Are we sure that there are not still new principles to be discovered in complex systems, biology and neuroscience? The root of the crisis in naturalism is its being wedded to the picture that the universe is a machine. This in turn is a consequence of the idea that nature is governed by laws which are timeless, immutable, and mathematical. The path out of the crisis is to embrace a new form of naturalism based on the reality of time and the evolution of laws. I call this temporal naturalism, a term I introduced elsewhere. Another indication of the crisis that afflicts all three manifestations is the growing fascination if not embrace, of multiverse cosmologies, according to which our universe is just one of a vast or infinite collection of other universes, within which the properties we have failed to explain like the parameters of the standard models of physics and cosmology, are distributed randomly. This surrender of the hope for sufficient reason, the hope to satisfy our curiosity as to the root of things. It is nothing but an indication that a philosophy wrongly assumed to be an essential part of science has failed. The remedy is not to throw away our hopes of understanding, but rather to discard our excess metaphysical baggage and to let science progress. To focus on this task, the first principle we adopt is that the universe is unique, single and singular. The uniqueness of the universe means there is just one causally connected domain, but we take it to mean more than this. We mean that the causally closed universe contains all that exists. The single unique universe must contain all of its causes, and there is nothing outside of it. This assertion, together with the reality of time, has a further implication, which is that there are no immutable laws, timeless and external to the universe, which somehow act as if from the outside to cause things to happen inside the universe. Instead, laws of nature must be fully part of the phenomena of nature. The distinction, absolute in physics till this point, between laws which act and states which are acted on, must break down. Laws evolve. Our most important point is that taking laws to be mutable and subject to evolution rather than timeless and immutable brings questions as to the choices nature has had to make about which laws govern the single universe within the domain of scientific explanation. We will show that this increases rather than decreases the empirical reach of our theories, because their hypotheses as to mechanisms which acted in the past to select the laws have consequences which are testable, not just in principle, but in real experiments. We will give several examples of such theories. When worked out in detail, these ideas lead to the denial of the Pythagorean dogma that the aim of physics is the discovery of a timeless mathematical object in every respect to the history of the universe. This leads to a third affirmation about mathematics rather than nature, which is that mathematics is an adjunct to scientific description of nature and is not a description of a separate or parallel reality or mode of existence, nor can any mathematical object serve as a complete mirror of the universe or its history, in the sense that every property of the universe is mapped to a property of that mathematical object. A key observation which is central to our argument is that it is fallacious to take methods and formal frameworks which have proved successful when applied to small subsystems of the universe and apply them to the universe as a whole. We demonstrate this by describing a precise schema for physics of subsystems, which we call the Newtonian paradigm, which includes the major theories of physics, including Newtonian dynamics, field theory, quantum mechanics, and general relativity, and show in detail how it breaks down when applied to the universe as a whole. This leads to paradoxes, fallacies, and dilemmas that plague the literature on theoretical cosmology. If we aspire to be scientific cosmologists, we must invent new paradigms of explanations. On the basis of this critique, we propose a direction for research to resolve the crisis facing our understanding of the whole universe. The place to begin is to assert that we do not now have anything that could suffice as an adequate theory of the whole universe. A substantial part of this essay is devoted to explaining that a theory of the whole universe cannot just be like the theories we know in physics, just scaled up to the whole universe. The universe as a whole is a very different kind of system from those usually studied and modeled in physics, and its comprehension will require a new paradigm, one that is novel, not just at the level of the content of the theory. One reason we need a new paradigm, apart from the fact that the usual paradigms break down when applied to cosmological questions, is that when we attempt to understand the whole universe, we face novel kinds of questions. These include the components of the why this universe question, particularly why these laws and why these initial conditions. The standard methodology of physics cannot address these questions because, as I will describe, it takes laws and initial conditions as inputs. A new kind of methodology and framework is needed to answer these questions. Therefore, the crisis that cosmology faces is not a crisis of a theory in progress. It is a birth crisis which accompanies our efforts to invent a new scientific methodology. The goal is the invention of a truly cosmological theory, which is to say, a theory that could apply to the whole universe and explain its features to us, including the choices of laws and initial conditions. It is often said that cosmology is in the midst of a golden age in which the quality and quantity of observations have increased dramatically. But anyone who attends a conference in theoretical cosmology may, hearing the range of speculation about multiverses, conclude that cosmology faces the greatest crisis of its short history, because those observations severely challenge our abilities to make sense of them. There are reasons behind both assertions. Is there a paradox, or are the celebrants and Boreas talking about different things? Indeed, there is no crisis in our attention if it is just restricted to the data itself. Looking back into our past, we can reconstruct a story of ceaseless change, which goes under the name of the standard Big Bang cosmology, which can model the observations using standard general relativity and quantum field theory. So the crisis is not located in the data, nor in any difficulty modeling the data in a way consistent with established principles of physics. The crisis is rather in attempts to go beyond modeling, to explain the data. It arises when we turn from describing the universe in which we live and understanding how it evolved according to the known laws of physics, and turn to a new question: why this universe? We confront crisis when we expand our ambitions from describing the part of the universe we can see to having a theory of the whole universe. To make this clear, let us distinguish between astronomy on the scale of the time since the Big Bang, which we can call large-scale astronomy, and the notion of the universe, by which we mean all that exists. The former we can also call our observable universe, to distinguish it from the universe, which may be very much larger. The great progress in observational astronomy concerns the description of our observable universe. The crisis concerns our knowledge of the whole universe. To make things clear, when I use the noun cosmology or the adjective cosmological, I will be referring to a theory of the whole universe. Unfortunately, some of what are usually called cosmological models are not cosmological in this sense. This kind of confusion is unavoidable, but to make the distinction clear, when I need to, I will call these models of large scale astronomy. Temporal naturalism, one way to frame the project of this book, advances, is to emphasize how fundamentally our conception of nature is shaped by our understanding of time. The notion of a law of nature is much changed if one thinks that the present moment and its passage are real or are illusions hiding a timeless reality. If one holds the latter view, then laws are part of the timeless substance of nature, whereas on the former view, this is impossible, as nothing can exist outside of time. Even the creed of naturalism, that is, that the natural world is all that exists, can mean two very different things, depending on whether you think existence is only real in each moment or only applies to timeless entities such as the history of the universe taken as one. To make this distinction clear, I propose to call the view we set out in this book natural or temporal naturalism, and to distinguish it from its opposite, timeless naturalism. Temporal naturalism holds that all that is real, the natural world, is real at a moment of time, which is one of a succession of moments. The future is not real, and there are no facts of the matter about it. The past consists of events or moments which have been real, and there is evidence of past moments in presently observable facts, such as fossils, structures, records, etc. Hence, there are statements about the past that can have truth values, even if they refer to nothing presently real. Well, it's the first entrance into Smolin. I think it went fine. I was a bit nervous for it to be monstrously more difficult. It is not. I think we're over the hill, and now it will be, I wouldn't say steep downwards, but not as tough. We've done the tough part now with Roberto, and now Smolin's is going to be helpful in broadening and deepening the understanding. And already now I can admit that a timeless universe, which I only a couple of months ago didn't even sort of ponder about, I think it was built in my experience, was an undubitable fact or undubitable experience, even stronger. But I'm seriously starting to doubt that. And that seeps into your very experience when Smolin and Unger opens those shut walls to understanding. I will end off with a picture of the World Trade Centers, how they shine in the sun. It's lovely. And here are some great bushes of rose nips. I'm going to take some of those now. Have a very pleasant afternoon, and bye bye for now.